This conference will now be recorded.
Okay, Deepa, we had already started with oil optics, and then we had learned in last two classes Huygens principle, and we had somewhat started with the interference part. And in the beginning, like in the last class, we had done superposition principle, and then we had somewhat learned what is called constructive and destructive interference, and also we know you need coherent sources for interference. So there are few conditions for a source to be coherent. So we'll discuss those things. Two coherent sources must be having same frequency, and it has to be monochromatic, like both the lights, both the rays should be monochromatic, and they should have constant phase relationship. So there are few conditions like that. So those things will we had already discussed. Today we'll find out conditions for constructive and destructive interference. So here today let us first find out conditions for constructive and destructive interference. So let us say there are two waves. Okay, so as I said, you need coherent source or coherent waves to have interference. Okay, so this we know. So suppose we have two waves which are coherent in nature. Coherent means they have to have same frequency. They have to have a constant phase relationship. So these are two main conditions, and along with that, they have to have only one wavelength. Okay, so I'm just taking. See here, what we'll do, we'll see destructive and constructive interference, like conditions for constructive and destructive interference. That means we have to find out some numerical expressions, and with which we'll be able to understand whether some places, if we have two waves, coherent, like coherent light waves, when they interfere, whether they will create constructive interference. That means the intensity after superposition will be maximum, or intensity after superposition will be minimum. Destructive interference means this will give minimum intensity, and upon constructive interference, that means upon superposition of two light waves, intensity will be maximum at the places of constructive interference. Okay, so we know these things from our previous classes. So today we are trying to find out mathematical expression in terms of wavelength, path difference, phase difference, etc. Okay. So let us take two such coherent light waves. Let us take two coherent waves. Okay, so one is having displacement y1, so which is given by a1 sine omega t. Okay, and the other one y2. Okay, y2 has the same frequency as I said, since they are coherent light waves. In fact, I'm saying light waves. Interference here in your course, interference for light is given, but this interference can, this expression whatever we are deriving now, this is common for any kind of wave, like you have sound wave basically. So sound wave, for any type of wave interference happens. Okay, and this expression is going to be general for any kind of waves which follow, like which are actually coherent in nature. They can exhibit interference. So I'm taking, see here also, here is actually the frequency, angular frequency is omega, so here must be angular frequency omega. But what I'm doing, I'm just deliberately putting some phase difference. But this, they have constant phase relationship. That means if the phase for the first wave changes by some amount, so this also has to change proportionately so that they can maintain the phase relationship. Or you can say broadly, or crude way, you can say the phase difference. Okay, so that they can maintain the phase difference. But this phase difference, when they actually have, actually they are emitting from the source. Okay, since they like from the point of generation to anywhere they go, they will maintain that phase relationship. So I'm taking this as omega t plus phi. So I'm saying that this is actually ahead of the previous one. So this y1, this wave by a phase angle phi. All right. So now superposition means, according to superposition principle, what we know, the resultant amplitude, if that is y, that will be actually the vector sum of the two. So this is what we know. Okay. For the time being, let us don't deal with the vector. We'll just go for the scalar expression. Now look, if I just do that summation, what you get, a sine omega t plus a sine omega t plus phi. Yeah, this is a2. Sorry, these are a1 and a2. The amplitudes are different. Now look here, we can use the identities of trigonometry. So what we'll do here, see a1 sine omega t is all right. I'll keep this as it is. Then here I'll write, see I know sine of a plus b, sine of a plus b will be sine a cos b will, so this is addition format. We'll just go for the multiplication format. Okay, sine a cos b, so here will be cos a cos b, sorry, cos a sine b. So this identity I am going to use here. Okay, so what is the identity I'm going to use? This identity. So this is the identity I'm going to use. So sine a plus b, this is the addition format. I'm going to multiplication format. So I can just write this sine omega t cos of phi, or okay, so plus cos of omega t sin phi. So this is what I have got now. Look, what I can do is I can do further simplification. So y is equal to y1 plus y2, what you are calculating is here actually a1 sin omega t plus a2. I'm just exactly writing the last line I have got there. So this will be uh, sin omega t cos of phi plus cos omega t into sin phi. So this is what we have got. Now look what I can do. I'll just take this sin omega t I have got common. Look here, a2 cos phi into sin omega t. Okay, sin omega t, and I can write this along with this. I'll keep like this: a2 cos of phi, sorry, sin of phi and cos omega t, sin of phi cos of omega t. Okay, okay. So look here, the same identity I can use if I put in place of a1 plus a2 cos phi. If I write this as r cos phi, let us say this is r cos phi, okay, and let us take this a2 sin phi, this as sin phi, okay. If I take that, let us see what we get. Okay, let us not take phi again, let us take theta. See, a1 plus a2 cos phi, this as a whole r cos theta, and this you take as r sin theta. So look, I'll rewrite. If I just put this term as, so I can get sin omega t, r sin omega t cos of theta plus here also if I put this, so r cos omega t into sin theta. See, look, r anyway will be common, so you get sin a cos b again here. Look, sin a cos b plus cos of a into sin b. The same identity here, it is in the form of multiplication. I am just writing in terms of addition. Look, sin omega t plus theta. Theta I can write, isn't it? So I get this wave. See, kind of same wave I have got here. Theta is a different factor, so this different phase angle. So theta I can get. How I can get theta? So theta will be tan inverse. Theta will be tan inverse. See, here I have taken sin theta by cos theta, right? So sin theta by cos theta. So sin theta is this a2 sin phi. So you will get here a2 sin phi divided by a1 plus a2 cos of phi. So this is the value of theta. Okay, this is separate, like different value than phi. Okay, what I'm trying to say is that we have to see, we had got after superposition we had got this expression, but this expression doesn't look like a single wave. You kind of see, you get sin omega t here, here cos omega t. So what you have to do, you have to make it as a single, either sin omega t or cos omega t, kind of that term. Okay, you have to write. So to convert into that, we are just doing this part, and also we don't have here in this expression, we don't have a unique amplitude, because we need to know intensity of the interference pattern. So to know intensity, you need to know the amplitude. So here you look, this amplitude I'll get as R. So what is R? Look, R square is equal to r square is equal to a1 plus a2 cos of phi whole square plus here a2 sine square phi. So this is the r square. If I get the square root of this term, look, the square root of this term, then I get the amplitude of this wave. So what I'm going to get is, I'm just writing here, you look, I'll just remove this part. The figure right hand side has some specific meaning, we'll just discuss that. Look here, what we had got, the resultant wave after superposition is, like, resultant displacement after superposition is this one, this, where r has to be found out. We don't know r, and that can be found out from here. See, r, what we get is this, see, square root of a1 plus a2 cos phi whole square plus a2 square sine square phi. Okay, so I'll just remove this part. Okay, look, if we solve this mathematical expression, the square root, this part, what we get, you will get a1 square plus a2 square, see, a2 square cos square phi plus a2 square sine square phi, that you get, right? And here 2a1 a2 cos of phi. Okay, I have done little bit of simplification. Okay, so what we have done, see, this is a1 square plus a2 square cos square phi plus 2 into a1 a2 cos phi, this term, and a2 square plus cos square phi, a2 square plus sine square phi, this will give you only a2 square. Okay, so what we can write is this, a1 square plus a2 square 2a1 a2 cos of phi under root of this. This is actually the amplitude of the resultant displacement. Okay, now see, if you want to find out what is the intensity, so intensity is actually proportional to the amplitude square. So we can write intensity is equal to some proportional to constant k r square. So r square means, again, this, you look, intensity will be then a1 square plus a2 square plus 2a1 a2 cos of phi. Okay, cos of phi. So what is the phi? Phi is the phase difference between the two waves. So now we have got the expression for the intensity. So I'll clean everything and then we'll write. So you just remember this. We have got r square is equal to a square plus a1 square plus a2 square plus 2a1 a2 cos phi whole to the power half. This is for, yeah, this is the value of r, and you have to do what? You have to find out intensity. Okay, intensity is directly proportional to r square, so which implies that this can be written as kr square. So on the right hand side we had a1 square plus a2 square plus 2a1 a2 cos of phi. So this is what we have got. Now look, what is a1 square? So if I multiply k both sides, okay, both sides, yeah, obviously both sides you have to multiply k so that equation remains the same. Anyway, so see Ka1 square. So this I can write as intensity of the first first individual wave, okay, first wave, okay, and similarly Ka2 square can be written as the intensity of the second wave. Like these are the individual intensities, and this is the resultant intensity after superposition. So finally what I get is this is, so K both side will go off, so you will get I1 plus I2 plus, see in terms of I, if you write A1 it will be under root of this, under root of I, okay, okay, A can be written, A1 can be written as under root of I. Similarly, so this will be the under root of I1, under root of I2, and this is cos of phi. So you get, so this is the general expression for the intensity of the superposed waves. Okay, when two waves, this is the general expression. I'll write what it is. This is the general expression for the resultant intensity after superposition. Okay, after superposition. Okay, so if you are thinking it is too hazy, I'm just cleaning everything. So what is the expression we have got? We have got the expression for the resultant intensity after superposition of two waves. So look, from here we have to find out the condition for, so since this is general expression, we can find out both the conditions for both constructive interference and conditions for destructive interference as well. Okay, look here, what we can do is we can, okay, let us clean. So we have got the expression for I1. So this is the resultant intensity. Expression for resultant intensity is this one. This is general expression when the two waves are having phase difference phi. So constructive interference. So now let us see condition for constructive interference. Constructive interference. Okay. So here for constructive interference, so I has to be, resultant intensity has to be maximum. Resultant intensity will be maximum at the place of constructive interference. So what is the condition for that? So what has to be the value of cos phi? If the cos phi has, if the cos phi has value, okay, cos phi has value plus 1, then only you can have maximum intensity over here, right? So for Imax, for Imax to happen, your cos phi has to be plus 1. Okay. Then what is the value of Imax? Maximum intensity. This is I1 plus I2, and then 2 into root over of I1 square root of I2. That's all. So now look, this expression can be written as whole square. Okay. I hope you won't deny this. Okay, let me write the intermediate line. So look, this means I only, right? So similarly, I can write square root of I2 whole square, and then you have 2 into AB. Okay, so that you get this one. Okay, so what you get for constructive interference, cos phi has to be plus 1. Okay, and see what is the intensity. This is the expression for intensity. Now you have to find out condition. So condition we have already written. What is this? Cos phi has to be plus 1. So how is it possible? How is it possible? Okay, so I'm just writing here again, cleaning. So condition for constructive interference. Okay, I'm just writing in short. So we have got anyway intensity has to be maximum. So that is given by this expression. So this you have to remember this, because in many places you will get, many competitive exam you will get problem, numerical problem, where you have to use this expression. So for that you have to have plus 1. Okay, so this will be plus 1. This, that means, see, this implies that your phi has to be either 0 or any even pi, 2 pi, 4 pi, 6 pi, like that. So that means what? In general, phi has to be in pi. Okay, so where, or you can write 2n pi. So where n is 0 or any integer number, like that. So this is the condition for constructive interference. Okay, so if we go with path difference, let us see how we can go. So you know, phase difference phi is equal to 2 pi by lambda, 2 pi by lambda into delta. Delta is the path difference. So if your phase difference is, see, phase difference is 2n pi, then what your delta has to be? What has to be path difference between the two waves? So look, I know 2n pi phase difference for this constructive interference to happen. Okay, so look, we know this is 2n pi, 2n pi, so multiplied by lambda by 2 pi. So what you get, 2 pi gets cancelled, you get n into lambda. So for constructive interference to happen, you can write conditions in terms of path difference, in terms of phase difference also. So in terms of path difference, your path difference has to be integral multiple of lambda. Integral multiple of lambda. See, integral multiple of lambda, where n is equal to 0, 1, 2, etc. we have taken. Okay, so these are two conditions. One with respect to phase difference, that is phi is equal to 2 pi n, and another one with respect to path difference, which is written as delta is equal to n lambda. N is the integer number in both cases, 0, 1, 2. It can go from 0 to any number. Okay, so here we can write, hence the resultant intensity at any point is maximum when the phase difference between two superposing wave is an even multiple of pi. As you can see, even multiple 2n pi, or path difference is an integral multiple of wavelength. This is the condition for constructive interference. So sometime in your board exam they can give you a short question that write down the expression for the constructive interference, or maybe in any places it may give, it may ask you to write the condition for constructive interference or destructive interference. So we have got the constructive interference, right? All right, so we'll find out the condition for destructive interference. Okay, let us do that. So I'll just do that here. Okay, because I have not allotted any uh, slide for that in the next. I'll just go before that. Okay, let us see. Let us first write the resultant intensity what we had got. So I1 plus I2 plus 2 into root over I1 into root over I2 and cos phi. This is what we had. So destructive. Now we are finding out the condition for destructive interference. Okay. So we have already found out condition for constructive interference. We will be finding out conditions for destructive interference. Okay. So for that you look, the intensity has to be minimum. Resultant intensity has to be minimum. Minimum means what? So cos phi has to be -1, then it will be minimum. Okay. So let us write minimum intensity will be this one. And you are intelligent enough to make it square, right? So it will be again written as this. Okay. So this is the intensity for destructive interference or minimum intensity where the destructive interference happens. Very nice. Now let us find out the condition for that to happen. So cos phi is equal to -1. So this happens when phi is any, see, any odd pi, any odd pi. So this is 5 pi, again 7 pi, etc. Okay, any odd pi. That means what we can write in general, phi has to be 2n plus 1 into pi. Okay, so look, in the previous case it was 2n pi, but here it is 2n plus 1 pi. So where you can write n is equal to, including 0, you can take 1, 2, 3, anything, any integer number. Okay, any integer number. Okay, now if you want to go with path difference, look, similar thing we will do, 2 pi by lambda into delta, which is path difference. So from here path difference will be lambda into phi by 2 pi. So phi we have already got. So what is the condition for phi? Condition with phi, this is 2n plus 1 into pi. Okay. So look, if we just strike this pi out, so what we get is delta is equal to 2n plus 1 into lambda by 2. So where n can be 0, 1, 2, 3, etc. any integer number. Alright, I hope you have got this point. So look, I'll just highlight this. So this is the condition for destructive interference when the phase difference between two waves become odd multiple of pi. And in terms of path difference, when the path difference between two waves will be odd integer or odd integral of lambda by 2, okay, or half wavelength. I'll just read it out. You just see, here's the resultant intensity at a point is minimum when the phase difference between two waves, two superposing waves, is an odd multiple of pi, or the path difference is an odd multiple of lambda by 2. So this is the condition for destructive interference. So if you ask me to write, yeah, make, so condition for, we'll write just conditions. Okay, so let me write condition for constructive interference together. I'll write together now. Constructive interference. So what we have got there, phase difference has to be 2 n pi, I should write 2 n pi. That means even integral of pi 2 n pi, okay, where n can be 0, 1, 2, 3, etc. Okay, and in terms of path difference, in terms of path difference, in terms of path difference, it is n lambda. Okay, it is n lambda. That means integral integer. Okay, integral multiple of wavelength. Okay, here also n can be either 0 or 1, 2, 3 with the same condition. Okay, so this is for constructive interference. So for conditions for destructive interference. So you might be thinking why sir is giving so much importance to this thing, because there are many problems in competitive exam from this part alone. Okay, if you remember the expression for maximum and minimum intensity, expression for this, the conditions for destructive or constructive interference, then it will be easier to solve numerical problem. Okay, so these are the conditions. Okay, all right, so with this we are concluding this part, constructive and conditions for constructive and destructive interference. Now we'll go to, like, we are going to learn what is interference in light, how we will be able to perceive this interference phenomena in case of light. And related to that, we have the famous experiment, Young's double slit experiment, which I'll just give some introduction today, because it is we have, I think, almost some 15 minutes. We'll have to finish between that time. Okay, so I'll give some introduction about Young's double slit experiment, but we'll be discussing what is called interference of light. So look, excuse me. So we have already learned interference means some kind of superposition of waves, and because of that, some places there will be maximum intensity, and some places there will be minimum intensity. So light wave means what? Light wave is electromagnetic wave, transverse wave, that is fine, but it has the same properties, like similar properties, wave properties, like it has frequency, wavelength, etc. So sound wave, light wave, they both can exhibit interference of light, interference. And in case of interference of light, when two light waves of same frequency and having constant phase relationship traveling in the same direction, they have to travel in the same direction, otherwise they cannot superpose. Okay, so traveling in the same direction, superpose each other, the intensity, then the intensity in the region of superposition gets redistributed. That means some intensity was there in the beginning for two waves. Okay, when they superpose at any point like this point. Okay, so the intensity gets redistributed. Okay, some places intensity becomes maximum, and some places minimum. Thus, a pattern of alternating dark and bright bands are produced. So this phenomenon is called interference. So in case of light, realizing the interference is very, very easy, because you know what you look when two waves having same frequency and constant phase relationship superpose each other. Some places it will create bright band like this. Okay, these are the bright bands where constructive interference is happening. The maximum intensity you will be able to find out here. And some places, see, these are the dark. If I write these are bright, I'll write bright, 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 and bright. And see here, these places. This is dark. This is dark. Okay, this is dark. This is dark. Like that, you look dark, bright, alternating dark and bright pattern will be like produced due to interference. So in case of light, it is an amazing phenomenon to observe in the lab. And in fact, when you go to your laboratory in your advanced classes, or maybe in this level also, there will be laboratory session where you will be able to see pattern like this. Okay, so interference pattern like this. This is with the red light, but generally in laboratory people do with sodium vapor lamp. Okay, so there in that case you will see yellow light. Anyway, you have to take, see, you have to take monochromatic light. See here, only one color you are able to see, right? So you have to see that your source has to be monochromatic in nature, monochromatic, and then both the waves, they have to have same frequency and constant phase relationship has to be there. So I'll just read the definition once again so that you understand again so better. When two light waves of the same frequency and having the constant phase relationship traveling in the same direction superpose each other, the intensity in the region of superposition gets redistributed. That means it is not like, see, where they superpose, it is not becoming like this. We have seen maximum intensity, we have find found out expression, right? This is becoming like this, isn't it? It is not just like addition. Okay, so if this would have happened, then you will not see this kind of alternating bright and dark pattern. You will see general illumination, like you you, you see when you like like illuminate any place with your torch. What you see, just a round shape, uniform light kind of that. Okay, so it is not the case here. Two light waves, when they are superposing, the intensity is getting redistributed, becoming maximum at some points and minimum at others. Thus a pattern of alternating dark and bright bands are produced. This phenomenon is called interference of light. Interference of light. Okay, I hope you have understood this. Now we'll go to Young's double slit experiment. See, as I said, uh, Thomas Young was the first person to do this famous experiment, double slit experiment, or experiment of light with the concept of wave, the, by the use of Huygens principle. Huygens principle was, or the wave theory was itself a doubtful thing until this experiment, Young's double slit experiment, was done. Or yeah, so here Huygens principle will be applicable very nicely, and this will see the interference pattern. What we see in nature could be produced by Young's artificially, like by creating artificially two coherent sources of light. Okay, so as you can see here in this experiment, as I said, you have to have a source of monochromatic light first of all. So yeah, so Thomas Young was the first person to demonstrate the experimentally interference of light, and that was 1801. In this experiment, a source of monochromatic light was used. See, it is it is called double slit experiment. Why double slit? I'll tell you what do you mean by slit. Suppose you take a cardboard which is opaque for light, and then you just make a rectangular, very fine rectangular hole like this. So this is called slit, denoted by S. See, when light comes like this, obviously here we will not go with the ray diagram. So, so suppose I have a source of light over here. Okay, source of light over here. So when this is suppose a point source, so light wave fronts, spherical wave fronts comes like this. Okay, and then the part of spherical wave front will be passing through this slit, rectangular slit. Okay, so part of it will be illuminated, and each point of that slit will be acting as secondary sources of, like, sources of secondary waves. Okay, see what I'm trying to say. What is called slit and all, you have to learn first, then we'll discuss what is called double slit experiment. See, this is opaque. Okay, light wave cannot pass through the opaque material. So for that, what you have to do, you have to make a hole, and this hole very fine hole, and that too rectangular in shape. So, or sometimes it can be a circular hole also. So this will give you, this is actually a slit. So when the light waves from any source comes as plane wave, or if you take a bulb, okay, so approximately, uh, so light will be, anyway, light will be actually passing through this as spherical wave. Okay, light will pass through it as spherical wave front, and then they will spread like this. Okay, from the source. So this is called fast slit S0. Okay, S0 or source SO. This is one slit. So what was happening? Sodium light was kept. If you keep it very far, then it will give you a plane wave. So see, first plane waves are coming, and suppose this is a slit where each point on the slit, okay, each point on the slit will act as point source. These are secondary sources of waves, and each of them will produce such kind of spherical wave front. And when you keep another slit, another opaque, making two slits now on that, so these are called slit 1, this is slit 2. So these are actually double slits on this opaque. So look, as you see from here, this is a general schematic for Young's double slit experiment. So sodium vapor lamp has been kept beyond, like, left hand side of this slit, and light, see, when the light is switched on, so light will pass through as spherical wave fronts from this first slit SO. And see, you can see these two slits S1 and S2 are illuminated by same wave front at a time. That means the sources you are creating S1 and S2, these two sources are actually illuminated by the same wave front. That means they will be definitely having constant phase relationship, they will be having same frequency. So these two waves, these two sources will be actually acting as coherent sources. So this is how he created coherent sources in the laboratory, and then what he done upon superposition, he has just kept one screen. So on the screen, what he could see is this kind of dark and bright bands he could see. Why? Because as I said, see, these two sources are actually acting as coherent sources, and I'll just draw it here. Coherent sources. So each point of these slits, each of them will act as point sources, and they will produce spherical wavefront. Okay. So suppose solid line and dotted line are actually, see, this is actually this is this is suppose straw, and this is actually, this is called sorry, so I just, okay, this is the maximum of the wave front, and this has minimum amplitude, this has maximum amplitude, and dotted lines has minimum amplitude, and similarly alternately it will progress like that. Okay, like this, it will progress like that. Okay, it will spread from that point. Similarly from here also, suppose first minimum amplitude, maximum amplitude, then again minimum, like that it will be spreading out. While spreading out, upon superposing, see, when they superpose with the same phase, they will give, so same phase in the sense either they are, okay, so you have this part and this part, right? So when both the waves will be superposing in phase, they will give you bright, and when they superpose out of phase, they will give dark bands. So this is how bright and dark band had been produced, or interference of light had been experimentally proved in laboratory by Young's double slit experiments. Okay, and in a very simple arrangement, you can see that very simple arrangement. Okay, by very simple arrangement. So today with this introduction, we'll stop it here. Next day what we'll do, we'll derive expression for the fringe width. See, you have dark and bright bands like this, right? Dark and bright. So dark and bright, dark and bright you have. So suppose this I take bright, then middle dark, then again bright, bright, this is bright again, bright, and look here, this is dark, this is dark, this is dark. So when you have like the width between two consecutive bright fringes, these are called fringes. Okay, fringes. So this fringe, like this separation between two bright or two dark fringe, will give you a, a lateral width of the fringes. So this is denoted by beta. So we'll find out the expression for that, and also we'll find out angular width of the fringes tomorrow. Okay, and many more small argumental, like argument basis problems or discussions we'll do with this experiment, like that expression and derivation. Okay, so we'll stop it here for today. We'll have class on again Wednesday on this topic. So bye for today.